All right, welcome. This is a video for Algebra 1, Unit 1 notes representing relationships. Section 1, we're going to call quantitative reasoning, okay? And what we want to get through is we want to describe a quantitative relationship shown in a table or graph, including graphs without scales, okay? Interpret a graph given with or without a scale to determine the quantitative relationship it describes. So the first thing I want to talk about is, but we have two graphs here, okay? In this graph, okay, notice that this doesn't have any numbers on the x-axis or the y-axis. So we would call this a graph that has no scale, okay? This graph has a scale, okay? It's got numbers here and numbers here, okay? To denote time and distance, okay? So what I want to talk about is a relationship between time and difference, or time and distance. So let me come in here. When I take a look at this graph here, okay, this shows me a relationship between time and distance. Okay, so what we see here is that we have time, values for time, and the distance traveled. Okay, so what we see here is at any point on the graph shows a value for time and distance traveled. Okay, so as we look at this, okay, as we look at this graph, what we notice is that as time goes on, distance changes, okay? At this point right here, at the point 0, 0, no time has elapsed and we haven't gone anywhere. But what we notice is that as time goes on, we travel a certain distance, okay, up to this point. And then all of a sudden, we travel a little bit further and further over this distance, and we travel further and further, to another distance. But then all of a sudden, this graph goes down. And so what I notice here is that from this point to this point, we travel forward. Okay? But from this point, that same point to this point, we travel backwards. Okay? So my goal for you guys is to be able to look at a graph and know what's going on. Okay? So let's take a look at an example down here. Okay? This talks about a turtle's distance from the start, okay, from where they start, okay? So what we want to do is just describe what's happening here. So as time goes on, between 0 and 6 seconds, okay, what we notice is that the distance is increasing. The distance is getting further and further away, okay? So when it wants to know is when's the distance increasing from the starting point, we can say that that's between 0 and 6 seconds. Okay? So we are increasing. We are going up. The distance is increasing. Okay? The second question says the turtle's distance from his starting point is constant. Now what that means is that the turtle doesn't move. Okay? The turtle doesn't move. All right, and what we notice is that when I look at this portion of the graph right here, we see that the distance doesn't change. We're not getting any further away, we're not getting any closer, okay? It's just constant, okay? And so this is a constant change, and that's between 6 and 8 seconds, okay, where the distance doesn't change. 6 and 8 seconds, okay? And then we want to know when is the distance decreasing? Okay, and it's decreasing if it's going down. All right, that means that we're going back. The distance is getting shorter. Okay, and that's between 8 and 12 seconds. Okay, so the one thing I do want to say about this is that when we go down, that means that we decrease. Okay, when we go up, we increase. Okay? Okay, next question says, examine the graph representing Lisa's activity and determine a possible scenario or imagined sequence of events relating the quantities of distance and time. Okay? So let's take a look at this graph. Okay, it says distance from Lisa's house. All right? And this is time in minutes. So what I notice is that at time 0, Lisa is pretty far from her house. Okay? As time goes on, as time increases, her distance from her house is decreasing, meaning she's going back home. Okay? And then from here to here, her distance doesn't change. It doesn't go up, it doesn't go down. It just stays constant. So at this point right here, she's not going anywhere. All right? And then all of a sudden at this time, then she rushes back to the house, and at this point she's home. So I'm going to label this graph, okay? So she's far away from home at this point. So far away from home. Okay? But then during this point, she starts traveling back home. Okay? So she travels back home. Okay? From this point to this point, okay, because her distance doesn't change, she's stopped. She's stopped. She's not going anywhere. Okay? Maybe she was at McDonald's. Maybe she was, getting some food. All right? Who knows? Okay? But she wasn't moving. All right? And then this very, very last point here, this is when she travels back home. Okay? And at this point right here, at this location right here, this is when she's at home. Okay? Okay, so are there times, the question is, are there times when the distance from Lisa's house is not changing or a constant? Okay? And that's this red portion right here. That's where she stopped. Okay? So then it says, are there times when Lisa's rate or distance traveled during segments of time seems faster or slower than others? Okay, now we noticed here, we said that here, that at this point she's traveling back home, and at this point she's traveling back home. Now, when we're talking about this rate, that's another word for slope. So when is the slope steepest? Okay? And that slope is steepest at the end in the blue part, so at the end. Okay? And when the slope is the steepest, that's when she's traveling fastest. Okay, so we look at the position, we look and see, okay, how are the y values changing when the x values are changing? But we're also sitting there going, okay, how steep are these lines? The steeper the lines, the faster she's going, okay, and vice versa. All right? So that's something to look at. So we're looking at where are the x and y values, and then also the steepness and slope of the lines. Okay? All right, let's take a look at the next one. All right, for his workout, Miguel ran uphill for a while, reached the top, rested for a few minutes to take a drink of water, and then ran back down the hill. Compare the graphs below and determine which one accurately represents Miguel's workout. Now, what I notice about these graphs is I notice that my label on the graph is total distance, okay? Not distance from home. So, you would maybe think that it's this one. And that, my friends, unfortunately, is wrong. Okay? Now, when you think of that, I'm going to go up a hill, I'm going to stop for a few minutes, and then I'm going to go back down the hill. That's what you would normally think about. But you have to think about something. You have to think about the total distance traveled, okay? When you walk up a hill, you're walking a distance, right? If you walk down a hill, you're still walking a distance, okay? Let's say that this is a mile, or meters. Let's just say that it's 1,000 meters, that you walk 1,000 meters. It's 1,000 meters up. How many meters down is it? It's 1,000 meters, right? But the question is, if you go up the hill and you go down the hill, are you all of a sudden, have you gone 0 meters? That's what that point means. When you look at this graph, this says total distance, you go up 1,000 meters, you don't go anywhere, and then you go backwards 1,000 meters, and you have walked 0 meters. That doesn't make sense, does it? Remember when we hiked up Mount Royal and you walked up, you walked a distance, and you came back down and you walked a distance? That's where you have to look at your label, and this says total distance, okay? And this value up here would maybe be 2,000 meters. And so this one is what you'd want to look at. All right, so on this next page, you have this graph here. The x-axis is time in minutes. The y-axis is total distance traveled in miles. Okay, we want to figure out which one of these scenarios represents the given graph. Now let's just take a look at the graph. What this graph says is that you start here, you haven't traveled anywhere, and you travel a distance, okay? And then, so let me zoom in on this, and let me write on here. Okay, so from here to here, you travel a distance, okay? Travel a distance. Okay? From here to here, you're stopped. Your distance isn't changing, okay? This is where you're stopped. Okay? And then, from here to here, you travel a distance. Okay? Your distance is getting further and further away. And then, from here to here, you are stopped. Your distance isn't changing. Okay? So it says, which scenario could be represented by the given graph? If you put the very, very last one, you are correct. Okay? Because it says, Ella drove to Bianca's house to pick her up. Well, in order to pick her up, she has to stop for a minute. And then they travel again to Una's house. And then they stop for a minute. Okay? So hopefully you got that. Hopefully that was good. Okay? Let's go ahead and check this one out. Okay? It says, determine and sketch the basic graph that would represent the table of values comparing temperature with the volume of gas. Okay, now what we notice here, folks, is that we don't have any values for temperature in degrees Celsius, nor do we have the volume, okay, of that gas. All right, so what we have is we have these values here. All right, and I have 10 through 90, and each of these differ by 20. Okay, that's something I notice about this. So what we're going to do is we're going to come in here and we're going to actually put those values in. Okay, I'm going to put 10 here. I'm going to put 30. I'm going to put 50. I'm going to put 70. And I'm going to put 90. Okay? And then we have these graphs. Okay? So we go from 90.7, 100.9, 111.1, 121.3, and then 131.5. Does anybody notice what these go up by? Was it 10.2 for each one? Okay. So as temperature, and here's the thing, as temperature increases by 20 each time, the volume increases by 10.2. Okay, now we can come here, and I'm just going to put in here, like, just say 90.7. I'm going to put in 100.9. I'm going to put in 111.1. I'm going to put in 121.3. I'm going to extend my graph up just a little bit because I'm a little off. 131.5. Okay? Now, as a result, I'm going to plot points here. Okay, so at 10, this is 90.7. Okay, when the temperature is 30 degrees, we're at 100.9 milliliters. Okay, when the temperature is 50 degrees, we are at 111.1. At 70 degrees, we're 121.3. At 90 degrees, we're 131.5. And because each of these numbers are the same, as temperature increases by a constant 20 degrees, all right, the volume increases by a constant of 10.2, okay? This is a constant rate of change. Therefore, we have a line, okay? So, and here's the thing, you know, temperature, these were x values, okay? Your volume was y values. And we can plot those on a graph, okay? All right, let's take a look at the next one, okay? I want you to go ahead and think about this and answer this on your own. Okay, so as I look at this graph, okay, here's my pressure, here's my volume. Now, as I move down this table, I have to ask myself, are the numbers getting bigger or are they getting smaller? And they're getting bigger. Okay, so as I look at these numbers, okay, these numbers are getting bigger. Okay? If the numbers are getting bigger, that means that it's increasing. Okay? And then I look at this side of the table and I say, okay, what's happening with these numbers? As I move down this table, are these numbers getting bigger or smaller? And they are getting smaller. If the numbers are getting smaller, we call that decreasing. Okay? So, here's what we've got. We just have to put that into words. And we have to say, as pressure increases, because this is what's happening here, the volume is decreasing. Okay, these numbers are getting bigger. That means that pressure is increasing. Volume numbers are getting smaller. That means that volume decreases. So your answer should be the third one. Okay? All right. Let's take a look at the next one. Okay? It says, Alexander and Lena were riding their mountain bikes on local trails. A portion of their activity is represented on the graph. Okay? So here you've got Lena's graph, and then on the dotted one you have Alexander's graph, okay? So it says, do the friends start at the same time and position? Okay? Well, if I look at this, what I see is that here at time 0, Lena has an elevation of 8. That's a pretty significant elevation, right? 8 miles. Riding a mountain bike, 8 miles up. I mean, what are we, 2? Not even 2? Yeah, I wonder who wrote this problem. I don't think they know what they're talking about. They should have been talking about this in feet, right? Kind of weird, right?
No, not feet, 8 feet.
Well, no, we'd be at like 10,000 feet or 9,000 feet. These numbers would have to be different.
Yeah.
See, you can make jokes and make fun of people based on their math skills. Okay, that's how it works. All right. Someone makes a bold claim that you're 8 miles up riding a mountain bike. Ain't happening. Okay. Anyways, I digress. Okay, but do their position? They start at the same position, but do they start at the same time? No. Yeah, you can say that they have the same position. Same position, different time. Different time. Okay? Is there any time when they cross paths? Yeah, that would be where they intersect, right? Yeah, so maybe at like 11.5 seconds, so at t equals 11.5, and then at t equals 15.5. Okay, and that's minutes. Okay, who takes the longest time to get from 8 miles to 1 mile above sea level? I can't believe this question. This drives me nuts. Okay, now here's the deal. Okay, if we look at Lena, it takes her about 18 minutes to get from, so it takes Lena is 18 minutes to go from 8 miles down to 1 mile. However, think about Alexander. He starts at 6 minutes, ends at 20. Okay, so Alex is 16 minutes, or no, 14 minutes. Okay, so Alex was actually faster. Okay, kind of interesting. Okay, let's keep moving on. Okay, on this one, again, what in the crap? Elevation, of 9 miles? Are you kidding me? Who are these people? Good grief. All right, well, let's just answer the questions, okay? Maybe it's on a different planet or something like that. Who knows? I don't even know. We're talking an airplane. If we're talking about airplanes, maybe. But we're not. We'll assume that this is airplanes. Okay, so at what elevation did Julio begin? That would be what? At his initial time when he started is 4 miles. Well, we're starting at 9,000 feet today, right? Isn't that where we're at? Yeah. Yeah. Yesterday I was in Denver. I started at 5,000 feet. That's when I woke up. That's when time began. Yeah. Yeah. Okay. At what elevation did Kathy begin? Kathy began at 0 miles. She was at sea level. Who made it to 8 miles first? So here's the thing. Let's take a look at 8 miles. Okay, here's 8 miles. Let's look at the graphs. Who made it first? Did Kathy make it first, or did Julio make it first? Kathy. In that time frame, we got to look at time values. Okay, so at this point, who made it first? 16 hours or 18 hours? So that would be Kathy. Okay. But who traveled the furthest distance? Okay. What we know, look at where Kathy starts. Kathy starts at 0, ends at 9. So Kathy, that's 9. Kathy did 9 miles. Okay, and I'm getting, those are Y values I'm looking at. All right. And then Julio starts at 4 and ends at 9. Julio traveled 5 miles. So Kathy is the one. You know, I like that name, Kathy. All right, let's take a look at the last 2 questions. On this first one, it says you have this graph of time in seconds. That's your x-axis, and your y-axis is speed in miles per hour. So this graph is different. Okay, we're not talking about a position graph. We're talking about a speed graph. Okay, all right. They start at the same location. Okay. Both cars start at the same location. It says, what can be determined about the speed of the car 1 compared to the car 2 over the first 6 seconds? Okay, so here's what we've got. Okay, here's our first 6 seconds. Okay, and here's car 1 going that direction. Here's car 2 for the first 6 seconds. Okay, what can we say about car 1 versus car 2? Car 1... So I'm going to say this. Car 1 is always faster over those first 2 seconds. Okay? Eventually, they do get to the same speed right there. Okay, do the cars intersect? Is the question. So a lot of you guys said yes, that they do intersect, okay? And that's a fair, assumption because of the fact that the graphs intersect, okay? But what you have to realize is that car 1 is traveling faster. We're talking about speed. We're not talking about distance. If this was a distance graph and they intersected, then yes, they would intersect. They would be at the same distance at the same time. But this is a speed graph, and what we notice is that these y values are always larger than these y values on this graph. So it's kind of a tricky question, but you really have to think about it in terms of, okay, this car is always traveling faster than this car. So they don't intersect. They don't intersect. Okay?
So are you saying just because, say, car 1's like faster, so then it'll pass you before car 2?
Car 1 is going faster. It's going to be ahead of car 2 the whole time. Eventually they will become the same speed, but we have no other information here. We don't know what's happening after 8 seconds. If car 2 were to end up, going up here and becoming faster than car 1, then yeah. But figuring out how far they travel based off of this graph is a calculus question. Okay? We can do it. We're just not going to. Okay? Yeah. Okay, so they don't intersect, and the reason why is because car 1 is always faster. Okay? That's kind of a hard question. All right? Okay, next one says determine which representation corresponds to the decreasing speed with an increasing time. Okay, so as I look at this, okay, we want to determine which one of these representations, okay, corresponds to a decreasing speed with an increasing time. So here's what I've got. Okay, as I look at these values for time here, they are getting bigger. Okay, so we're increasing. Increasing. Okay? And then what we notice here is that the values of my speed, those numbers are going to get bigger. Each time they're getting bigger. Okay, so they get big, so we increase. Okay? So Simon drives faster as he enters the freeway from the entrance ramp. Okay? Does that show a decreasing speed? No, our speed is increasing. Okay, our numbers are getting bigger. But if we look at this graph, and sorry it doesn't show it, but this is a value of speed, and this is time. Okay? And so then, what we notice here is that the speed is decreasing. Okay? So as time gets bigger, okay, what are the values doing on my speed? Okay, and those are going down, those are getting smaller. Okay, so this situation would be the correct representation of a decreasing speed with an increasing time. Okay? That's all I got for this. This will be uploaded on the internets.